Language models are at the core of natural language processing, serving as the backbone for countless applications like text generation, translation, summarization, and more. Language models are designed to predict what comes next. If you think about how you finish someone's sentence in a conversation or predict the next word in a phrase, that's exactly what language models aim to do, only they do it mathematically. In this episode, we'll explore the journey of language modeling, starting with simpler statistical approaches like n-grams and Markov models, and progressing to the transformative deep learning models like GPT and BERT, which are the foundation of modern NLP. Let's start with the basics, n-grams. An n-gram is essentially a sequence of n consecutive words or tokens in a text. For instance, in the sentence, I love natural language processing, a 2-gram or bigram would be I love natural, and so on. By counting how often these n-grams occur in a large corpus of text, a language model can predict the likelihood of a given sequence. For example, after seeing I love, the model might predict you or pizza as plausible next words. While n-grams are simple and intuitive, they have significant limitations. For one, they require a large amount of memory to store all the possible sequences, especially as n increases. More importantly, n-grams struggle with long-range dependencies. They can only remember the immediate context, so they might fail to capture broader relationships in a sentence or document. Markov models build on this idea, adding a probabilistic layer. In a Markov model, the assumption is that the probability of the next state, like the next word, depends only on the current state or a few preceding states. This is known as the Markov assumption. For example, in predicting the next word after I love, the model might only consider I and love without looking further back. Markov models are great for capturing local patterns and sequences, but like n-grams, they struggle with understanding context over longer spans of text. These early methods laid important groundwork, but their limitations highlighted the need for something more sophisticated. Enter deep learning. Deep learning revolutionized language modeling by moving beyond simple frequency counts and fixed context windows. Neural networks, particularly recurrent neural networks, brought the ability to process sequences of arbitrary length, allowing models to learn from entire sentences, paragraphs, or even documents. RNNs work by maintaining a hidden state that carries information about previous inputs as they process each new token. This hidden state acts like a memory, helping the model understand context over longer sequences. However, RNNs aren't perfect. They suffer from issues like vanishing gradients, which make it hard for them to remember very distant information in a sequence. The next leap came with attention mechanisms and transformers, which solved many of these issues and propelled language modeling into an entirely new era. Transformers, introduced in a landmark paper titled Attention is All You Need, discard the sequential processing of RNNs in favor of a parallelized approach. At the heart of the transformer architecture is the attention mechanism, which allows the model to focus on specific parts of the input text when making predictions. For example, in translating the sentence, she saw a dog and it barked loudly, the model can use attention to link it to dog, even though several words separate them. This ability to capture long-range dependencies and relationships is what makes transformers so powerful. Transformers paved the way for models like GPT, Generative Pre-trained Transformer, and BERT, bidirectional encoder representations from transformers. GPT is designed primarily for generating text. It's a unidirectional model, meaning it predicts the next token based on the sequence of tokens that come before it. This makes GPT particularly adept at tasks like story writing, conversation, and code generation. BERT, on the other hand, is bidirectional, meaning it considers both the tokens before and after a given token when processing text. This bidirectional understanding makes BERT excel at tasks like question answering and sentiment analysis, where context on both sides of a word or phrase is crucial. What's remarkable about these models is their versatility. GPT can write essays, create poems, and even generate computer code. BERT powers search engines, helping them understand the nuances of your queries. Both models are pre-trained on massive datasets, learning general language patterns before being fine-tuned for specific tasks. This pre-training approach makes them incredibly efficient and adaptable, capable of achieving state-of-the-art results across a wide range of applications. So what's the key takeaway here? Language models have come a long way, from simple statistical methods like n-grams and Markov models to the deep learning powerhouses we use today. At their core, all language models aim to understand and generate human language, but their capabilities have expanded exponentially as our techniques have evolved. Modern models like GPT and BERT don't just process text, they understand it in ways that were once unimaginable, capturing context, relationships, and even nuances like tone or intent. As we continue in this series, we'll dive deeper into how these models are built and how you can leverage them for your own NLP projects. This is the power of language modeling, turning words into insights, predictions, and creations that transform the way we interact with technology.